Hello everybody, and welcome back to another geometry lesson. Today we're going to be taking a look at 8.2, which is all about the angle-angle similarity theorem. As you can see, these notes are very brief. They're going to go over one theorem and a couple of examples. So, let's get started. First things first, let's talk about what makes two triangles similar. You might recall from the last lesson, we said that two shapes are similar if all their angles are congruent and if all the sides were proportional. It had to be both of them that are true in order for triangles to be similar. With triangles, though, we have some exceptions. You see, with triangles, we don't need both things to be true. It's either or. So, if all angles are congruent, or if all sides are proportional, the triangles are similar. Doesn't need to be both. The angle-angle similarity theorem actually challenges this as well, makes it even better for us. The angle-angle similarity theorem actually says we don't even need all angles to be congruent. We just need two. If two angles of a triangle are congruent to two angles of another, then the triangles are similar, guaranteed. I want to explore this idea a little bit because it might not seem evident at first why that is. So we're actually going to prove the angle-angle similarity theorem, which means we can't use it as one of our reasons. We're trying to prove it just with what we knew before this theorem. So let's see what we're given. We are told that angle A is congruent to angle D, and that angle B is congruent to angle E. Those are our given pieces of information. And somehow we need to show that these two triangles are similar. Well, we might recall that there is a theorem from all the way back in, I think it was Unit 5, that talked about two triangles with two angles each. The theorem went like this. Since all triangles add up to 180 degrees, if you know two of them, then you can solve for the last one. The name of that theorem was called the third angles theorem. The third angles theorem says if two angles of a triangle are congruent, the third angle on the triangles must be congruent. Angle C is congruent to angle F. That is the third angles theorem. Now, that we know that the three angles are the same on both of them, wasn't one of our restrictions that if all angles are congruent, then the triangles are similar? So we can say that triangle ABC has to be similar to DEF, since one of our definitions of triangle similarity, definition of similar triangles, was that all angles had to be congruent. So there we go. That is a proof of how we could do this. Very nice. Let's take a look at example 2. So I'm going to show you how to do the first example, and you're going to try out the next two. We have to determine whether the triangles are similar, and spoiler alert, they are. It then says to write a triangle similarity statement, which will look just like the proven statement in our proof. One triangle is similar to another. So looking at example A, right now we're trying to find two angles that are congruent. Here's one. We know that angle D has got to be congruent to angle G, since all right angles are congruent. Cool. Beyond that, we're stuck, because the angles we're given don't match. Unless they're not supposed to. You see, the only restriction was that two angles had to be the same. It didn't say which two. Let's see if we could solve for our missing angle K on this triangle. We know that all triangles add up to 180, so 90 plus 64 plus the measure of angle K equals 180. In other words, 154 plus K should equal 180. So what's the measure of angle K? 26 degrees. And if this is 26, doesn't that match this angle here? So we can actually say that angle C is congruent to angle K. Our triangle similarity statement would be, because of AA similarity theorem, we can say that triangle CDE is similar to, well, since C is similar to K, we'll start with K. Since D is similar to G, we'll go to G, and then throw in the H at the end. Perfect. I'd like you to pause the video here and see if you can do exercises B and C on your own. Pause here and come back when you're done. Let's do these together. So, in this first example, we see that we have two triangles, but they're kind of hard to see. I'm going to redraw them just for our convenience, and for another reason. So triangle AEB is the one that looks like this. And we know that angle B is congruent to angle C on triangle ADC, right? Is there another angle that has to be the same across both of them? Well, while it may not be obvious at first, we can use the reflexive property because both triangles share the same angle A. You see how both these triangles have A as their top measure? And A is congruent to A. So since A is congruent to A and B is congruent to C, we can say that the two triangles are similar. ABE is similar to ACD. Likewise, in C, we can solve for some of these angles. Right away, I know that these two angles will be the same because they're vertical. So angle SVR is going to be congruent to angle UVT. And when we look for other congruent angles, we can think of these lines, these two parallel lines, as being cut through by a common transversal. That line right there cuts through both of them. So we know that angles R and T are going to be congruent because of alternate interior angles. Angle R is congruent to angle T. So similarly, we can say that triangle SVR is similar to triangle UVT. Perfect. Last problem, folks. We have a word problem, and we need to know how to contextualize word problems. So here we go. A flagpole casts a shadow that is 50 feet long. At the same time, a woman standing nearby who is 5 foot 4 inches casts a shadow that's 40 inches long. And we want to see how tall the flagpole is to the nearest foot. Always, when you end up in a situation like this, I recommend drawing a diagram. So the diagram for this one would look like this. We have our flagpole here. There's our beautiful waving flag. And we know that it casts a shadow that is 50 feet long. I'll use purple to represent the shadow. Cool. I'll label this as 50 feet. And I'll label the flagpole as X, since we don't really know how tall the flagpole is. Nearby, we have a woman who is standing here. I'll draw her like so. And her shadow is a bit smaller. It's 40 inches long. But we also know her height is 5 foot 4 inches. And we somehow need to figure out what X is. You might be tempted to jump straight into the math, but the first things first. I don't see any similar triangles in this diagram. We have to recognize that the similar triangles are found by connecting the end of the shadow to the head of the person and the end of the shadow to the tip of the flagpole. What would these red lines represent? Well, it will represent the shadow cast by the sun's rays. Obviously, there wouldn't be two suns, but we know that these two rays would be the same. Okay, I'm convinced that these are triangles, but I'm not convinced they're similar triangles. We've already seen from our Mona Lisa problem last class that sometimes things can be deceiving. Well, what we do know is there are some angles that are the same here. No matter what, the angle formed by something standing up and the ground is a right angle. So those angles are the same. Is there another angle that we know is the same? Well, the sun's rays are going to hit each object at about the same angle. So we do have two similar angles. Because we have two angles in each triangle that are congruent, we know these triangles are similar. So that's the first thing we've shown. Since we know the triangles are similar, we could find a scale factor or set up a proportion. Since we need more practice with proportions, I'm going to choose to set it up that way. So, first things first, I cannot set up a proportion when I have 5 foot 4 inches as one of the measurements. The flagpole's measurements are in feet, so this will be X feet tall. The woman's measurements should be in inches. So 5 foot 4 in inches is 64 inches. Now we could set up a proportion. We could say the woman's height compared to the flagpole's height is proportional to the flagpole's shadow compared to the woman's shadow. We could say shadow divided by shadow is meant to equal, I apologize, my marker is just dried out, is meant to equal the height of the flagpole divided by the woman's height. It's okay if the units are a mismatch. When you're setting up a proportion, it doesn't matter. If you were doing a scale factor, it might matter. But if you're setting up a proportion, these units will resolve themselves anyways. They'll cancel each other out. So let's do it. Let's cross multiply. We can do 50 times 64 and 40 times x. 50 times 64 is a bit difficult, but we know that it's going to be 3,200. We have 40x, so we just have to divide both sides by 40. X equals 80 feet. And even if you converted everything in this problem to inches or everything in this problem to feet, you're going to get that the flagpole's height is 80 feet. I recommend trying it out if you don't believe me. With that said, everybody, that will conclude our lesson for today. Thank you so much, and have a great rest of your day.